Hey everyone, saw an interesting problem on Reddit the other day pertaining to op amps. Someone posted their exam from a summer course and asked for a little help understanding how a circuit worked. Given that my copy of DaveCAD just arrived straight from Australia, I figured now would be a great time to do a little demonstration video of it. But you know what I always say, don't solve the equation, just kind of wing it. Now, I don't know how you were taught to solve circuits or how op amps work, but the way I got it was a little bit obtuse. All these new complex terms like inverting terminal and high input impedance and infinite gain feedback resistor made no sense to me. So I've come up with a bit of an analogy that will hopefully make it a little easier to explain. Let's say we're constructing a building and we need to lift packages and equipment from the ground to different floors on the building. We're going to need a crane. Now, this crane can lift up to 18 tons and it's operated by a man who sits in the cab. There's another man who waits on the floor for packages, and he radios down the crane operator to let him know how close the packages are getting. If you can imagine the crane operator being a little bit heavy-handed on the controls, he might accidentally overshoot the target, especially if the load's only 500 pounds and doesn't use all of the 18-ton capacity. That's okay though, the radio man will be able to provide feedback for the crane operator. The radio man holds his hand apart to indicate the distance the package needs to go. When his hands touch together, the crane operator knows he's right on target. This is a pretty good analogy for an op amp, so let's start breaking it down. Obviously, the crane in this story is the op amp. The desired floor for the package is our input signal, and the current height of the package is the output signal. The man standing on the building is the feedback resistor, and the crane operator represents the internals of the integrated circuit. The first thing to realize is that neither the crane operator nor the radio man exert any effort in this. All the work is done by the motor, or in our case here, the power supply. The idea is that measurement and amplification of our signal should not affect the signal itself. Think back to a voltmeter. You may recall that an ideal voltmeter has infinite resistance. That's because we don't want to draw current from our circuit affecting the reading at a particular node. In the same way, the op amp has high input impedance so as not to disturb the input signal. We'll talk more on this later. The second thing to understand is that the goal of the crane operator is to make the radio man's hands touch together. He can either tell the crane to go up or down in a bit of a binary way, and he knows he can stop when the radio man's hands touch. In the same way, the op amp's goal is to make the voltages on the terminals equal. Let's look at an example here of an inverting op amp. We'll slow down time so that you can see the current actually flowing into the circuit. Let's start by saying the voltages everywhere are zero. As I apply voltage to the input of the circuit, the potential travels across the input resistor here. The op amp notices a difference between the terminals. One's at a positive and the other is at ground. Now, the only way the op amp can rectify this is by lowering the output potential here to draw current through the feedback resistor. Because the op amp has infinite gain, it may sink a huge lug of current in an attempt to lower the output voltage quickly. It might overshoot by a little bit, but because it's constantly monitoring the voltages at both input terminals, it can compensate for this. You'll notice I just explained to you the two magic rules of op amps, except there was reason behind it. It's a bit of a dangerous analogy though, because there's probably quite a bit wrong with it. For now, forget everything I just said. Let's do a little bit of math. Now, the first thing to remember is that the op amp is going to want to make the difference between the input terminals zero. Since this is an ideal op amp, we'll pretend this happens immediately and without any of the problems mentioned before. Now, if we set the non-inverting terminal to a particular potential, the 0-volt difference means that, well, when the op amp is settled, the inverting terminal will also be at that potential. For now, we'll ground the non-inverting terminal to make this a more traditional problem. This lets us say that the voltage at this node here will be 0. Given this, we can solve for the current that flows across the input resistor using Ohm's law. Vin minus 0 volts divided by Rin gives us I. Now, we know, using our op amp rules, that no current will flow into the input terminals. So, all the current, by Kirchhoff's current law, has to flow up across the feedback resistor. Using the same principles, we'll solve for our second unknown, and then for Vout in terms of Vn. Now, there's an interesting thing to notice about the result. Whatever we send in this circuit comes out multiplied by a negative constant. The inverting op amp is a very popular configuration, and you'll see it quite often throughout your designs. In your head, you can sometimes block off the whole circuit into a black box or a sub-circuit. This drastically simplifies analyzing a circuit and will help you decide if your result makes sense. So, with that out of the way, let's take a look at the circuit in question. Off the cuff, this circuit looks pretty ugly. Part of the problem, though, is how the circuit's drawn. If you stretch this resistor up here, you can start to recognize patterns and divide the circuit into blocks. Right here is an inverting op amp, here's another, and this looks like a voltage divider. Well, this circuit just got a lot easier to solve. There are two hitches, though. The first problem is that circuit number 1 is dependent on circuit number 2. Circuit number 2 is dependent on circuit number 1, so you have a bit of a control loop. Even still, this isn't too difficult to solve if you keep a cool head. You end up with 3 equations and 3 unknowns. But one question is, what about this little resistor over here? Turns out this is just a red herring. I guess MuzzyBear's teacher just didn't like him or something and wanted to throw a tricky problem in the batch. Having an intuitive grasp of circuit function is really quite useful. Let's take a look at the second problem. It gets ugly real fast. There's inductors, and that means phasors and j-omegas. Do not want. I have to admit, I even flinched when I looked at this circuit, but the first 2 problems are a cinch. The first thing is to recognize that this is simply a fancy way of drawing an op amp. For sanity's sake, I've replaced it. Much better. The first question asked is, what if we input a very high frequency? Well, we know that the inductors become open circuits at HF, so let's just erase this temporarily. These resistors add, and there you have an inverting op amp again. Your gain becomes R feedback over R input, with a negative. What about DC? Well, the inductor turns into a wire and shorts our feedback resistor. Since our feedback is now 0, our gain is now 0. Another way to look at this is to say that when the inductor becomes a wire, it shorts out these resistances. Remember, the op amp is going to try and make the difference between the terminals 0. Therefore, this node, and consequently the output, must be 0. Well, that was super simple, and we didn't even touch a radian. The latter part of this problem asks you to solve for the transfer equation given an input with a particular frequency. Rats, now we have to touch the j-omegas. The secret to this part really comes from redrawing the circuit. I just don't like the way it looks here on paper, and I think it'd be a lot easier to understand if we reorganize things a little bit. You have to be careful about doing this because if you make mistakes like I did, well, you get the wrong answer. The secret to solving this problem is to turn everything into an impedance. The difference between impedance and resistance is that impedance is dependent on frequency. If you draw everything as little boxes like this and just treat them as resistors, it shouldn't be too hard to solve. Exercise left to the reader. Well, I hope that makes op amps a little easier to understand. I know I didn't get them the first time until I started playing with them. I've got a bit of a theory that engineers don't understand anything until they play with it and subsequently blow it up, but that's just me. I might try to do a few more of these depending on how much free time I've got. Big thanks to Dave Jones from the EEV blog and Chew from Chew Tech. I know I've learned a lot from their videos. So, I'll see you next time. Thanks for watching.